Good morning, everyone. My name is Stefan Mattern from DYNAmore. Welcome to this week's DYNAmore Express. Before we start, I may kindly ask you to keep your microphone switched off during the session. I will do this later for everybody as well. If you have any questions, please post them into the chat. So we will try to collect them, and if there is time in the end of the session, we will have a quick Q&A at the end of the session. Also, in the end of the session, I will post a link to an evaluation form, and I may kindly ask you to evaluate our seminar. And with this being said, I want to hand over to my colleague, Dr. Filipe Andrade, who is giving a presentation on probably the most popular and most widely used material model, LS DYNA, and I will pass the ball to him. Are you here?
Yes, I'm here. I will start the presentation. So, good morning, everyone. And my name is Filipe Andrade. And I will be here today, your host, giving this talk about Mat24. I hope everyone can see my first slide and can hear me well. And as Stefan already said, if you have questions, you can put them into our chat, and then we can see if we have some time for answering them. If we don't have enough time for all of the questions, you can always send us an email to our support from DYNAmore, and we can, of course, help you. So I'd like to start by talking a little bit about my title, Good Old Mat24. I chose it like this because it's a little bit the feeling that we have towards this material model. I see this a lot in customers. They have a lot of confidence in Mat24. Everybody thinks it's a model which is quite reliable, robust. You never get an error termination because of Mat24. And sometimes when you don't know what to do, which material model you have to use, people very often just go back to Mat24 and try to do something with that. And that's why I thought, well, that might be an interesting thing to review it a little bit here today. I still believe it's probably the most popular material model in LS DYNA. I'm not really sure, but especially for crash, of course, for other applications like material forming, then you might have other material models that are more popular than Mat24, but anyway, it's very, very often used by LS DYNA users. So, oh yes, and one thing I would like to mention, many of the things that I'm going to show you here today, they don't only apply for Mat24. So some of the things that we have, they apply for other material models as well. So you can see this talk not only about Mat24, but some things that we have in LS DYNA and that you also have in other material models. Some of the things that we're gonna see, it's exactly the same in other material models in LS DYNA. So I'd like to start here first, giving you here my outline. I will start with a very short review of the theory behind Mat24. It's just one slide. It's not much more than that. And then I will show you the keyword of Mat24. We'll talk a little bit about how to work with the load curves for this material model. And then we have a certain discussion about how to formulate strain rate dependence through the VP flag that you have in the keyword of Mat24. We will talk about the internal handling of curves and tables. And finally, I will make some final remarks regarding Mat24. Try to give you a few hints and tips. Very often I'm asked, what is the best practice? What should I do? What should I take care of? Is there something that I should avoid? I try to give you a few guidelines regarding this. Also during the presentation, I will mention some of the things that I've seen over the years, things that I think there are important, and other things that, well, some things the user has to decide what is his strategy towards the material modeling. So let's start here with this very little theory that we have. Actually, MET24 is based on the so-called J2-based plasticity. This kind of model, a plasticity model, has many names. It's also very popularly known as the von Mises plasticity model. Some authors prefer J2 because, well, it's more general. Not only von Mises made contributions to the model that we have today. But anyway, so these are the two typical names for this material model. And we start here with the yield function that tells us when it starts to plastically flow. So the yield function in MET24 is actually quite simple. It's just the equivalent stress, also known as the von Mises stress, minus the yield stress, which can be a function of the plastic strain. This plastic strain is the equivalent plastic strain which is accumulated throughout the deformation process. And basically what MET24 does, or any J2-based plasticity algorithm, it checks first if the yield function, if it's satisfied or not. Yes, and if, for instance, if the equivalent stress is bigger than the current yield stress, then you have to use the algorithm in order to calculate how much of that deformation is plastic and how much is elastic. So if you plot this yield function in the principal stress space, you have a cylinder, and this is a good thing for MET24 or for the J2-based plasticity model, because we don't have any sharp corners that might give us a bad derivative. So one of the reasons why MET24 is so efficient and so robust, that's one of the reasons, and not the only reason, but one of the reasons is that smoothness of the yield locus. It's very, very smooth. You don't have any problems with your derivatives whatsoever. And then when you decide that, well, I am plastic, there's something that we call the flow rule. And the flow rule basically tells you how much plasticity you have in that deformation state. And it's given by this, just make my pointer here. Is your pointer? Yes. So plasticity is basically given by this here, or the flow rule. You have here, this is the plastic strain tensor in its rate form. So you have here the plastic multiplier and also this derivative. And in the case of the von Mises model or MET24, this derivative is actually quite simple. So that's the expression for the flow rule for MET24. And you as a user, you don't have to know this, but I just like to mention this because this expression here is actually quite simple in comparison to other models. Sometimes users want to use a more sophisticated model. For instance, they just add some other dependency here in the yield function. And the result is that this function here gets much more complicated. This derivative here can get much more complicated than that, just that. So sometimes you make just a small change here in the yield function, and the consequences in the flow rule are quite dramatic. So that's one of the reasons why if you sometimes you just try to get a little bit away from MET24, you try to use another material model, it gets, for instance, more difficult to solve numerically because the consequences of small changes in the yield function can be quite dramatic later on the flow rule, which tells you how much plasticity you have in your deformation. But in the case of MET24, well, in the numerical algorithm, if in the case you have no rate dependence, basically you can calculate what is the plastic strain increment through this very simple expression here. So basically that's what we have implemented in the code, something similar to that. It's just a very simple scalar equation that you have to calculate, and you get your plastic strain increment. So this is very simple and very easy. It's not always true for other material models. Other material models, they might be quite more complicated than that. And that's why sometimes when people just change from Mat24 to something else, they notice that they are needing more computational time. And the typical, what people say is, well, this new material model is too slow. I think it's more like Mat24 is extremely fast. And one of the reasons is because of the simplicity of the model. In case of viscoplasticity, you cannot do just that. You need to do an iterative procedure. And of course, this takes a little bit longer. But I would say nowadays, this is quite acceptable. It's quite reasonable to make it that way as well. But even in the viscoplastic case, Mat24, it's much, much simpler to deal with that, with this viscoplasticity, than other material models. So one of the reasons why Mat24 is so robust and efficient, it's coming from here. It's coming from the formulation, from the model. If you ever wondered why we don't use too much Tresca, Tresca's yield function for plasticity, it's because Tresca actually, if you look here at this plane, actually Tresca has some sharp corners in his yield function, and those sharp corners, they give you the derivative is no longer unique, and then you have problems. Okay, so the consequence of using von Mises or Tresca as an yield criterion is perhaps not very big, just for checking if there's plasticity or not. But the algorithm later on, using Tresca's yield function, is much more complicated than using the von Mises one. So here we have the keyword definition in LS DYNA. So Mat24, it's officially called piecewise linear plasticity. You can use both of them. You can use Mat24, you can use piecewise linear plasticity. LS DYNA understand both of them. And here, of course, typically to any material model, you have the material ID, you have the density, you have the Young's modulus, and the Poisson's ratio. So these are the 3 or 4 first entries here in the keyword. Then you have sigma y, which is the yield stress, and E10, so it's the hardening modulus, but only in case you want to use a simple linear hardening rule. If you want to use something else, my big recommendation is to use a load curve. So you can put here the ID of this load curve there. In LS DYNA, you understand well, that's the stress strain curve, the true stress, true strain curve for the plasticity. We have some other flags here, like the fail flag, which gives me a failure strain. That's the equivalent plastic strain at failure. It's something that you can use. Many users use this for general failure description. It's something that I do not really recommend, because this failure strain is the same for all possible stress states. So you have the same failure at strain failure for tension and compression, for instance, which we know that it's not really true from experiments. So keep in mind that when you use that failure criterion, it's a very, very simple failure criterion. And if you need something a little bit more sophisticated, something a little bit more realistic, then you have to use some other criteria or a damage model like Gizmo. We also have here CP, LCSR, and VP. All these flags are related to strain rate effects. CP, these are the so-called Copper-Simons parameters. LCSR, it's a curve that you can define where you have scaling factors as a function of the strain rate. So you can use your single hardening curve, and you can and it's multiplied by factors which are a function of the strain rates, something that you can do. And the VP flag, VP stands for viscoplasticity. You can tell us then if you want to use viscoplasticity or not. We're just going to see later on a little bit about this. And then we have here 2 lines which are historically there. I do not necessarily recommend you to use those lines. You can use them. It's not an error, but I think in the meantime, you can use the load curve. It's more flexible. It's more general. But here, basically, you can input your hardening curve with 8 points. You put here the strains and here the stresses. But again, I think nowadays we all can use load curves. And I think most of the customers I know, all of them are using load curves. And by the way, part of the success of Mat24 is also because of this kind of input, that you can input here a load curve instead of analytical function. It gives you a lot of flexibility, a lot of freedom for using the curves that you need. So I think that this kind of input is certainly part of the success of Mat24 over all these years. So how can we define the hardening? The easiest way is by using a single load curve. When I write here recommended, I mean load curves. You can also use tables. Okay, so I recommend you to use curves or tables for your input. Even if you use an analytical expression, you can just calculate what would be the curve, and you can input them here in Mat24. It's very simple. Here you have the idea of the load curve, which in this case here it's exactly 100. And here in this slide, I have exactly, these are the points, the pairs of points. I have here the strains and the stresses. And it's a one-to-one correlation to this curve here, which is plotted here. And you see here, I don't have too many points. And here we see why it's called piecewise linear, because between 2 points, LS DYNA will always linearly interpolate. So the quality of your curve depends on the resolution of your curve. So if you have more points, you will have a better quality of your curve. You have less points, you have a worse resolution of your curve. So you have here this flexibility of defining how many points you want to use. Basically, there's no limit in using points. You can use as much as you want. The only limitation is your hardware, so you need enough memory for using all those points. And of course, for a single material card, this makes almost no sense. You can put millions of points inside there. But if you have many material cards, then it starts to play a role. If all your cards are extremely fine defined, then this might play a role in your memory when you're doing your simulations. So it's quite simple to use this. At this point, I like to mention a common mistake that I've seen quite a few times over the years. Sometimes people have the hardening curve as an include, and they just forget. It even happened to me. It's not that untypical that you forget, and by mistake, you just have here one blank line at the end of the curve. And sometimes you don't see it. You just hit enter and you didn't see that you have a blank line. Well, if you have this kind of blank line and nothing else, what happens is that, well, LS DYNA will interpret this blank line as default values. The default values are 0 and 0. And this means that that blank line will give you a point here. So you have here a very beautiful hardening curve, but then you have the 0, 0 point. And what LS DYNA does is, well, it linearly interpolates between the points, and then you might have something like this. And of course, this can lead to error terminations. So my recommendation when working with curves, with curves in include files is you can always use asterisk end at the end of your files, so you can be sure that there's no blank line left in your curves. Yes. So here now, let's talk a little bit about the strain rate effects. There are different ways of doing this in LS DYNA. There are two things that you have, or that you have to carry here. Or yes, one thing is how to introduce the effect of the strain rates, or what is the information about the strain rate effect. And the other thing is, what is the formulation you want to use to consider those effects? So these are two separate things. Sometimes it leads a little bit to confusion. I try to explain here. Well, if you want to consider this dependency of this information about the dependency of the strain rate, well, there are different ways. One way is using the so-called Cooper-Simons parameters. Basically, these are C and P, and these are parameters which are governed by this equation here. And this equation here is also a function of the strain rate. And basically what you have here is a scaling factor, and this scaling factor will scale your yield curve depending on the strain rate. In the end, if you evaluate this equation, you see that you have a kind of exponential behavior of this rule. I would say, well, those Cooper-Simons parameters, this idea is quite old. Actually, I think it's from the 60s. I would say that nowadays you can use a better solution, which are tables. You can use a table to define the strain rate dependence. And basically, you use exactly the same flag here as you did for the single hardening curve, with the difference that now you have several hardening curves. You have a different hardening curve for each strain rates that you have. And I think most customers are using this option. It's also the option I'm most familiar with actual problems. So I also suggest you to use that. Gives you also more flexibility when defining the strain rate dependence. In the meantime, at least in my experience with steels, a simple scaling of the quasi-static hardening curve is not enough to fully describe the strain rate dependence of the material. And that's basically what these Cooper-Simons parameters are doing. They are just scaling the quasi-static curve. And again, in my experience, materials don't really behave like that. It's a bit more complicated, but you have this freedom to do so using a table. You also have here the LCSR curve, which basically, as I said before, it's just a curve with scaling factors as a function of the strain rate. It's something that you can also do. But again, I think the table solution is the most practical, flexible, and probably the best one. And finally, well, this here is the way how you define this dependency. What is the effect of the strain rate? What's the effect that I'm waiting or expecting? And then you have the VP flag that tells you about how to use that information to effectively introduce the effect of the strain rate. Now, again, VP stands basically for viscoplasticity. The original model was 0, so there was no viscoplasticity. And we still have that today in our code. And basically, when you have VP0, you have a scaling of the yield stress. And this yield stress is simply scaled. And to that scaling, for that scaling, we use the total strain rate. Okay, so you have the elastic strain rate and the plastic strain rate inside of your strain rate, which is used for the strain rate dependence. Now, for metallic materials, or at least for steels, you don't really see that. You see that the plastic strain is actually the driving force for the strain rate dependence. So we have this other formulation, VP1, which is the viscoplastic formulation. It uses the plastic strain rate, but in order for that to work, you need iterations. You need to iterate. Otherwise, it does not work. But basically, those iterations are necessary to divide how much of the strain rate is plastic and how much is elastic. And in this regard, using the table, we have a very robust and very efficient algorithm that in a very efficient way looks up the table that you have, looking for the correct stress at the correct strain rate, and it works very well. And last but not least, we have also this option VP3, which is quite like VP0, but there's a difference. Now we filter the total strain rate. It's a relatively new feature. For shell elements, you already have it in release 9.3. some customers are already using this their everyday job. And if you want to use that for solids, well, then you need to use a very new LS DYNA version. It's not that long that it's available there. And although I will not talk too much about this feature, I can tell you that for the filtering, you have to set up this value here, C. And this value C is no longer, if you have VP3, is no longer the Copper-Simons parameter C, but is the filter that you choose. It can be chosen between 0 and 1. Yes, and again, some customers are already using those this feature. I think there are some differences, but a big difference is that VP3 can better deal with curves which are intersecting each other. Sometimes you have this, so that the curves are intersecting each other, and VP3 seems to be a quite robust solution for that case. The viscoplastic formulation has some problems with that depending on the level of intersection. So VP3 can be used in those cases. So what is the effect in the end for the user if you use VP0, VP1, or VP3? Well, one thing that we can see is the effect of, of relaxation. Relaxation can only be calculated if you have viscoplasticity, also because it's closer to the physical phenomenon that is behind the strain rate dependence. So here we have just a very academic example where we load an element or something like this, and we apply a certain displacement over time, and we have a strain rate dependent material, okay? And then at a certain point, we just keep the displacement constant, and we just leave like this. We just leave it to relax. And if you do this in LS DYNA with VP0, what you get is that it abruptly goes back to the solution, to the quasi-static solution. There's no relaxation whatsoever, which is something that we do not observe in experiments. With the viscoplastic formulation, you do get a nice relaxation over the time. So in the end, this effect is, of course, more physical. When it comes to VP3, I have to be honest, I never did that test. So I'm not 100% sure what would be the effect. But one thing is that I don't believe you're going to have this viscoplastic relaxation with VP3. But because of the filtering of the strain rate, I'm also not sure that it will really happen like abruptly like this case. So this is something I still have to test at some point. But I cannot believe that you're going to have the same viscoplastic relaxation like in VP1. So VP1 is, in essence, of course, more closer to the physical phenomenon that we want to simulate here. Well, with the strain rate dependence. So here I have a practical example. What happens when you use VP0, VP1? I have just a tensile test. I just pulled it vertically, and I made the simulation with VP0 and VP1. And what you see first, the solution with VP0 is slightly over the solution with VP1. The reason for this is quite simple. You're using here the total strain rate, not only the plastic strain rate. So that's part of the reason. If you use VP1, you're correcting that effect. So you're only using the plastic strain rate, and that's why you get a curve which is slightly below the VP0 curve. And what we can see here, especially if we zoom in, is that VP0 is giving us some oscillations throughout the formation, and in VP1 we get a very nice and smooth solution. And this is again coming also from this from the algorithm. VP0 does not consider that part of that strain rate will be plastic and part will be elastic. It uses everything. So throughout the incremental procedure in the finite element method, you get sometimes a solution which is actually too high for the reality, sometimes it's too low, and then you get those kinds of oscillations. It depends on the material, on the strain rate, on many things, the level of these oscillations. If you have very low strain rates, then the oscillation tends to be not as pronounced as in other cases. But the thing is that you do have those oscillations, and when we are talking about dynamic problems, oscillations can always be a problem. So a kind of recommendation that we give to our customers is trying to use VP1 whenever possible. But we know that many customers use VP0 for different reasons. Sometimes they have old validated material cards with VP0, so they can keep using them. But if you're starting a new material card from scratch and you don't have to use intersecting load curves, then our recommendation is always to use VP1 for the calibration of your material card. In the case of VP3, which I don't have it here today, but basically, if you don't set the filter, you get a solution which is quite close to VP0. And if you start using the filter, you can get rid of this oscillation a little bit. And if you really push it to the limits, at least for the uniaxial tensile test, you can even reproduce the solution with VP1, which at first glance always looks like, okay, VP3 can be like VP1. Well, it's not entirely true. It's true for a monotonic loading like this, like in uniaxial condition. But if you have load reversal or if you have bending, then VP3 still behaves differently than VP1. So I would say that VP3, it's kind of a compromise between VP0 and VP1. Okay, so how can I define a table in Mat24 or in general? It's simple. You have just used to here, your ID now will be a table ID. And in this table ID, you can put here the strain rates, which are the true strain rates. Very important to mention this. Sometimes people just use the nominal strain rate that they got from the experiment. That's not really correct here. LS DYNA is expecting the true strain rate. And if you just use it like this is the typical definition most people are using, most customers are using, just define table. The logic is like this. You have the strain rate here. The sequence of the strain rate is important for the sequence of the defined curves here. So this first strain rate is related to the first curve. That strain rate is related to the second curve, and so on. Well, normally, if you open this card in LS Prepost, you're not going to see, you're going just to see a group of curves. But you have to imagine that in reality, what we have is like a three-dimensional space. So for every strain rate, you have a different curve, and you can even just plot that three-dimensional surface. And basically, that's what LS DYNA is doing when it's solving the when my Mat24 is being used with strain rate dependence. You have that surface, and especially in the case of VP1, you're iterating inside that surface. And again, for that case, we have a special algorithm which looks just for parts of that surface in order to make it more efficient. So there's no big deal here in doing this with the tables. One question is, well, we know that in the direction of the plastic strain, I already told you this, we have a linear interpolation between the points, but the jump from one plastic strain to the other is generally very small. So we can live with the linear interpolation. But one question is, what happens in the strain rate direction? Well, in the strain rate direction, you have basically two options in LS DYNA. You can either interpolate it linearly, or you can interpolate logarithmically. You have both options. And I summarized here in the slide how you do this. Well, if you want to use the linear interpolation, all you have to do is you just use here mat piecewise linear plasticity. You just define your table with your real strain rates. Here I'm using, my strain rate measures is per millisecond. So here per second would be 10 and 150 per second. So you just put the values there, and this time we understand it. As the real strain rate. If you want to work with logarithmic interpolation, there are two ways. Yeah, there's the old way. Many old material cards have this already implemented. And how do you do this? Well, LS DYNA will interpret as a logarithmic interpolation if the first value in the table is negative. And if this first value is negative, LS DYNA will interpret like this. This value here is not really the strain rate, but the result of the logarithm of the strain rates that you want. So here, if I want a strain rate of 0.01, if I do the logarithm of it, I will get minus 4.6, whatever. And that's the value that I have to input there. The same thing here. For 0.15, I do the logarithm of it. I get this result, and I put it there. Okay. At a certain point, if you have values which are bigger, larger than 1, then you have positive values. It doesn't matter. LS DYNA will understand. It's only important that you have the first value to be negative. So this means that your first strain rate in your table for that kind of modeling has to be less than 1, depending on your unit system. That might be, that should be no problem. And there's well, it's not that new anymore. We have this for a few years now. You can always use this option called log interpolation. And if you put this, LS DYNA will just interpret this as the real strain rates, and will perform the logarithmic calculation internally. So you don't have to input anymore the logarithm of the strain rate. You just put the strain rate, and LS DYNA will calculate that for you accordingly. And that's over the years now, over the last years, customers which are making new material cards, they are definitely preferring this way of using, if they want the logarithmic interpolation, of course, because it's more readable. You can just look at the material card and you know what are the strain rates that you have in your table. So basically, you can use any of these options. There's no restrictions. They give you basically the same result. It doesn't always give you the same result for very, very low strain rates, because sometimes users tend to write here the first strain rates to be 0. There's no logarithm of 0. It's infinity, minus infinity, and then LS DYNA has an internal rule for calculating a certain strain rate, which I don't remember anymore what it is, but it's something else. You cannot just use 0 there, or you can. LS DYNA will do something else, and that's a problem that you don't have it here, because basically at a certain point there's a maximum number that you can input here. So minus infinity cannot be input here with this classical way of inputting here the logarithmic interpolation. So here are a few remarks on the handling of curves and tables in LS DYNA. I'm not sure if you know this, but generally what we do in LS DYNA is that the material curves are rediscretized by default. So basically, if you have this curve here in the input, LS DYNA will take the first point and the last point, will divide it in intervals which are of the same size. And depending on how many points you have in your rediscretized curve, you might get something like this. So your fine resolved curve here just loses resolution because of the internal rediscretization. And this sometimes may lead to results that are not expected by the user. So I'd like to remember you, or inform you, that we do this. We do this for basically for performance issues. It's faster if you have curves which have a equally spaced number of points. And that's why it's done. There's this flag here, this keyword in LS DYNA called control solution. And there's this flag called LC int. This is the number of intervals that you have here. The default is actually 100. But what we recommend is to increase that value. A typical value used is 1001. You can increase that value as much as you want, or decrease. In our experience, 1000 or 1001 is already a quite good value for most cases. So you can try using this. There's also no limitation here. You can increase this value as much as you want. The only limitation is your memory. If you might run problems with memory. For a single material card, of course, that's not a big deal, but many customers of us They have very large models, and a typical approach is, for instance, that you just, because it's simpler from the process, that you have all material cards in all models that you have. It doesn't matter if these material cards are being used or not. It's simpler from the process point of view. And if you have a very high LC int, then you might get into problems, in memory problems from your hardware. So you need to choose a reasonable value, but again, in our experience, 1000, 1001 is a good value. 1001 sounds a little bit strange. For Mat24, it doesn't really matter too much if you use 1000, 1001. It's more interesting if you have curves for some material models like rubber or so, where you have a positive and a negative side. So with 1001, you can be sure that you have a value exactly at 0. So that's the reason why we recommend this. So sometimes you want to be sure, okay, what is LS DYNA using in my simulation? Because I have this rediscretization. I want to see what it's really using. There's a way of doing this. Here in control output, you have this flag called IP curve, which is per default 0. You can switch this to 1. And if you switch this to 1, LS DYNA will output all the digitized curves in your D3HSP file. This can be helpful in order to evaluate or assess if your curve has been rediscretized well or not. Well, with well, I mean if this rediscretization is still similar to your original curve. Sometimes it might change your curve in a way that you don't want to. So the way of debugging this is by using this feature of LS DYNA. I have to warn again that if you have quite a lot of material cards inside your model and you activate this flag, your D3HSP file can get quite long. So you have to see if it's a valuable solution for you or not. Big customers with big models, they normally don't use this option. Otherwise, they have a very, very large file. But you can activate this, especially when you are trying to debug something to see if the curve which is being used by LS DYNA is a curve that that is reasonable enough. For hardening curves, probably that doesn't play much of a role. The rediscretization is normally well, but I see a bigger effect when people try to put a limit on a curve. This is typical, for instance, for the strain rate dependence of the failure, where you have the failure up to, I don't know, a strain rate of 1 or 100, and then you want to keep the strain rates dependence from 100 and above. You want to keep it constant. People just choose a factor of 1000 because it sounds logical from go to 100 to 1000. And because of the rediscretization, you lose some information from the lower strain rate. So yeah, so in that case, you can debug and see if the rediscretization is changing too much your curve by activating this option in LS DYNA. So you can check if your rediscretized curve is like the original curve that you had in your input. Still talking about rediscretization, when you only have one curve, like here, then there's no internal rediscretization in general. So LS DYNA just takes the curves as it is, so there's no much of a problem here. If you start using a table, then we have two different behaviors. The first behavior is what happens in VP0 and also VP3. You have a rediscretization in the direction of the plastic string, but you also have a rediscretization in the direction of the strain rate. And depending on the number of LCN, this might change a little bit your input. Yes, especially for lower strain rates, because normally the values of the lowest strain rates, they are quite small in comparison to the other values. You might lose some resolution exactly at the beginning of your table. And in the case of VP1, we have a rediscretization of the points in the plastic strain direction, but no internal rediscretization in the strain rates direction. So this is a big difference, actually. again, especially for lower strain rates, where things here are quite nonlinear at the beginning. If you run it with VP0 and VP1, of course, you see the effect of viscoplasticity, but you also see the effect of using a different curve than you wanted because of the internal rediscretization. So this is something that you have to bear in mind in your simulations. At this point, we recommend, it's not necessary, MET24 will accept it anyway, and in the general case, I would say it will work well, but our general recommendation is to use the same number of points for all strain rate dependent hardening curves. It's a recommendation. You don't have to. Again, I already made some tests. It does work if you don't do that. But by using different number of points, you might get surfaces that are in the space, in the three-dimensional space, they don't make too much sense. So you can kind of make it a little bit better if you use the same number of points for all curves. Again, it's a recommendation. It's not a need. LS DYNA will accept it anyway. And then here a little bit to the subject of extrapolation of curves, something that we are also asked very often. How does LS DYNA behave? Some softwares, they just, when the curve is comes to the end, they just keep it like a constant, a horizontal. That's not the behavior of LS DYNA. LS DYNA always takes the two last points of the curve. Only those two last points. It calculates what is the something like the stiffness here, the last slope of the curve, and we'll take that last slope and we'll linearly extrapolate. So if you need a strain, a plastic strain which is 2, it will not keep using that same last value, but it will use the extrapolated value. So this is very important. That's the standard behavior in LS DYNA. If you want to enforce that you have a horizontal line for the extrapolation, you need to choose these two last points in such a way that the slope is horizontal as well. Okay, and again, because of the rediscretization, if you want to do this, don't just do like a point like a 2, because otherwise LS DYNA will just rediscretize also this zone between 1 and 2, and you don't really want to do that. So one smart thing, or one good hint is just add a little bit to the last plastic strain value, and then you get the horizontal as you want. So this is a typical way of doing this when it comes to the extrapolation of curves. And perhaps now another hint, this happens sometimes. I've seen it a few times. You have a curve like this. The curve looks at first glance quite good, and you don't see why is there any problem there. But then if you zoom it, you will notice that, well, those two last points were actually gave you a negative slope. Only those two, for instance. Yeah. And because it gives you a last slope which is negative, LS DYNA will extrapolate linearly, and you might get you just go down here, and depending on the position of those points, you can even get suddenly values which are quite close to 0, or even 0 or negative. In hardening curves, it doesn't happen that often. It happens a lot, for instance, when working with failure, working with the dependence of the strain rate on failure. Sometimes people just have the last slope. They have a curve like this, and it stops like this. Perhaps I try to draw a little bit. They have a curve like this, and just stops like this. And suddenly they have a strain rate which is much higher than the one that they predicted, and they have something like this. And then you have a sudden failure in your model, and you don't know why. It's just because of that extrapolation. So these are things that you have to take care a little bit. And for the strain rate dependence of failure, can always do something like this. Sometimes you just don't have more information after that point. So a good hint or a good tip is just try to keep it constant. It can help a lot in your simulation. So again, LS DYNA always extrapolates linearly, after using the last slope. This is important. Well, and finally, I have here just one slide about typical procedure, how to calibrate a yield curve. There are different ways, and it's not my goal here today to discuss this into detail. We have some courses where we discuss this more in more detail. I'm just showing here one way of doing this. Normally, when we do material cards for our customers, that's the method that we use. And basically what we do is for typical metallic material, we have tensile tests, and up to the necking point, we just, because we are uniaxial, we just convert this engineering stress strain curve to a true plastic strain curve. So we remove the elastic part, and we also convert from the engineering strain to true stress and true strain. So we do this up to the necking point. To the necking point, we know that's the solution. It's uniaxial. We can show analytically that that's the solution. So that point of the curve is basically already known and defined. And for the point after that, when we start having the necking, the localization, then we need to extrapolate somehow. There are several methods of doing this. A typical method is you calibrate your model numerically. So I have here one practical example. The black curve is my experiment, and I start first with that extrapolation. This is just the trial that I have. So that's my first hardening curve. So you can see here, that's basically my necking point. And from that point on, I just try it out with a certain extrapolation. That's the red one. And if I simulate my tensile test with that curve, I get this response here. So I'm way away from the experiment. So I know that my curve here is not, it's too soft. So I need to increase its stiffness, so to speak. And what I can do is, okay, I will try with the next curve, like the green one. And if I simulate it again, I will see that, well, it gets better, but I'm still not there. And I can keep doing this until I can reach, for instance, this solution of the purple curve. And as you can see here in this case, I'm much closer to the experiment. It's a typical procedure. You don't have to do it like this. Some customers prefer other methods. That's the method that we mostly use. And what we do also, which is not shown here, in the meantime, we always have, we measure the strains locally, optically, with a DAC method. And we compare the strain fields that we have here in the simulation with the experiment, in order to be sure that we are really describing the material behavior. And this works very often very well. So this is a typical way of doing this. So the curve that you want to put in your MET24 can be calibrated, for instance, using this kind of method. And finally, I have here just a few more comments, additional options in MET24. Perhaps you don't know some of them. The option _2D. Well, that's something that a lot of people don't know, but in MET24, even if you're working with shells, we are using all the transverse shear stresses for calculating the equivalent stress. And not all material models behave like this, or especially if you are using different codes, not every code does that. So MET24 in that respect for shells is not like 100% plane stress. You still have the effect of the transverse shear stresses. And if you want to deactivate this, you can use this _2D function. Then you will disregard the transverse shear stresses in the definition of the equivalent stress. Depending on your loading or load case or your application, you will see an effect or not. Another option is this mid-fail option. So if you use that failure flag in LS DYNA, basically the failure flag is valid for all integration points of your element, which is not always a good idea. So with this mid-fail option, you can enforce LS DYNA to check the failure only in the mid plane of the element. Of course, this is only valid for shell elements. And the stochastic function allows you to make a variation of the yield and failure behavior inside of your structure. So you might have at one point more or less yielding behavior or more or less failure. This is something that you can do with the option stochastic. And finally, I have here also 4 material models which are similar and very often used by some users, like MET 123. It's basically MET 24, but it has an additional or has additional enhanced failure criteria. For instance, the thinning of your specimen or the major strain, something that you don't have in MET 24. MET 224 gives you it's like MET 24 as well, but you also have the temperature dependence also in tabular format, so you can use curves and tables as you're used to in MET 24. You also have a failure criterion there, which is kind of close to what you have in Gizmo, very similar. So it's also enhanced in comparison to the typical failure criterion that you have MET 24. 225 has a very simple kinematic hardening rule implemented. So I suggest customers to use this, especially when they suspect that kinematic hardening may play a role in their application. So I think this is a first step. You just get your MET 24 card, you add some kinematic hardening just to see in the simulation what is the effect. And then you can have a better idea if the kinematic hardening is playing a role in your simulation or not. I already had a few cases where this was really the case, and later on the customers decided to use a more sophisticated kinematic hardening model. And the last one is MET 251. It's being more and more used by our customers. You have basically MET 24, you have the dependence on the plastic strain, on the strain rate, and you can add an additional dependence, for instance, the hardness or whatever you want. Basically, you can just say to LS DYNA, I want to use that history variable to be a further dependence in my table. So in the end, you don't have a table 2D, you have a table 3D, so you can add other dependencies as you want. So I will finish here my talk with a few final remarks. I think most of them we already talked here. LS DYNA is very fast, it's very reliable, very robust. That's why it's the workhorse in crash simulations. It is available for shells, solids, beams, virtually for all element types in LS DYNA. The load curve-based input makes this material quite flexible, and I think this is part of the success of this material model. You don't have kinematic hardening in this material model, but again, I just mentioned this 225 is basically MET 24, but you can also add the kinematic hardening. Basically, if you don't have viscoplasticity activated, the plasticity routine does not make any iterations. This is a quite good approach for explicit analysis, but sometimes some customers had problems in implicit analysis because the steps were too large in their implicit simulations, and they start having some accuracy issues because it was not iterating. So a hint for you, in case you want to do this, you can set this flag IACC to 1 in control accuracy, and this will make MET 24 always iterate. It doesn't matter if you have viscoplasticity or not. This is but this is only valid for implicit analysis. Something I would recommend for that case. Well, the other things we already talked about: interpolation between the strain rate dependent curves, either linearly or logarithmically. Some people ask me what is the best choice. Well, I don't know. It's up to you. Some people prefer this or that. The only thing I can say is that a well-resolved 3D surface for the plasticity will give you in general better results in your simulation. So the logarithmically option does that more easily than the linear. But if you use linear interpolation, you can also generate as many curves as you want, and you can also get the necessary resolution. Extrapolations, always linear, using the last slope of the curve. one thing that I didn't mention is that there's no extrapolation in the direction of strain rates. It doesn't matter if it's in each direction. The lowest curve and the highest curve, they will always be the limit of your strain rate dependence. And finally, negative and zero slopes, they are permitted, but should be avoided. You can use them. It's not a problem in LS DYNA. But if you do this, our recommendation is that you know what you're doing, because whenever you set a negative slope, you can run into problems. You will not necessarily to, but you can. So using monotonically increasing curves gives you more robustness, more numerical robustness in your model. So I would like to thank you for your attention. I didn't check the chat if there are questions. Perhaps we can answer quite just a few, and if not, you can always send an email to our support. So thank you very much.
Yeah, thank you, Filipe. I will steal the presentation board from you just for a minute. Thank you again for this interesting talk on MAT24. And I just posted the link to the evaluation form in the chat for everyone. So please take a minute or two to fill out this evaluation form for us. You can re-watch the video of this webinar if you want. We will put it to our YouTube channel in the next days, and you can also check out the slides following this link here. Oh no, you don't see the link, right? Sorry, I have to share.
I think you only sent to me, right?
So now you see something, right? So
okay, yeah.
I think I was talking about. Okay. So, and if you have any questions, I've just seen that there popped up one question in the chat. Oh no, some more. Let's take probably one or two questions from the chat. Is this okay, Filipe?
Yes, of course.
There is one question. You can read it by yourself. For plastic materials, how does this model compare with MAT89? Can you answer this?
Yeah, it's a good question, because to be honest, I don't use MAT89. So I'm just taking here a look at the manual, and it says MAT89 is the same as MAT24 except for the following points. Oh yeah, the load curve lookup for yield stress is based on equivalent uniaxial strains. Okay, failure depends on strain rates and so on. So okay, basically the formulation is similar, but the way how you define what is the driving quantity is not the plastic strain as MAT24, but the so-called uniaxial plastic uniaxial strain. So it's a little bit different, but the formulation itself should be similar to MAT24. I have another question here for input of table of for MAT24. Do we need to use true strain rates or engineering strain rates? You have to use true strain rates. That's what LS DYNA interprets. How can I display the strain rates to particular time point of the elements? Contour plot. Yes, you can. There are two ways you can define. If you're using strain rate dependence, the first history variable of MAT24 is the strain rate. And you just click on the element and you evaluate that. Another method is if you have the plastic strain in LS pre-post, you just evaluate the plastic strain and you make the derivative of this over the time, and then you also get the strain rate, and basically it's the same thing if you use the history or this method. The only difference is perhaps the output rate, but basically it's the same thing.
Okay, Filipe, thank you very much again. Since it is always past 10, I think we will close the session for today. If you have any more questions, please feel free to write an email to us, and please have a look at our website and our other sites where we collect LS DYNA examples, papers from the conferences, and so on. So please.
I'm sorry, Stefan, I don't remember if you said, but those slides will be available later also on our website, because it was also a question here only to me.
Yeah, I said it, but I didn't show the link. This is the link where you will find the slides. They're not there yet, but in the next days, probably uploaded there, and you can just. Okay, so this is it. Thank you very much for your time, and I wish you a nice weekend and a nice holiday, and we again next time.
Yeah, thank you very much for your attention, and perhaps we will see each other personally in some time in the future.